Hi everyone. I'm Filippo. I work on the Go team at Google, and I've done various networking and cryptography work in the past. But today we're here to have a look at doing networking with the net package in Go. Now, before we start, as a show of hands, who here has ever used the net package directly? Not through net HTTP, not through gRPC, but directly importing net and using netcon, netlisten, directly working with connections. That's not a lot of hands, and that's a good thing for two reasons. One reason is that it means that we're providing you with the high-level interfaces that you need to get your work done without working directly with connections. And the other reason this is good is that what we're going to do today is look at how to use the net package to implement a useful program directly dealing with the connections. Now, before we go into using the package, I want to talk for a bit about networking in Go. Because networking in Go is a bit of its own special thing. And to understand why, I want to take a step back and look at how it used to work in other older systems. So for a long time, an option has been to build threading servers. The scenario here is that you have a server, you want to accept some connections, and you want to serve them. And you would like to be able to serve more than one connection at the same time, more than one client at the same time from the same server. One option is that every time that a connection comes in, you start a new thread. A thread is essentially a kernel-level process that shares some memory with the original program. And the important thing for what we care about is there's a lot of small differences between processes and threads, but what we care about is that the kernel does all the scheduling for threads. So we just run our code, we just run our code sequentially, and the kernel will take our thread and put it on the various CPUs when it needs to run code, and take it off when it needs to run something else on the same CPU. Now, the disadvantage of this is that threads are not that lightweight. Threads will come with a whole system stack, which can be it can be 2-4 megabytes, depending on how your system is set up. And it will take the kernel scheduling your thread. And every time your thread comes in and out of the CPU, it has to freeze all the state that you need to go back to executing that. So over time, a new pattern developed, which is called the event loop. Popular high-performance programs like nginx use this pattern. How this works is that instead of having one thread per each connection for each client that you're trying to serve with your server, you're going to have a pool of threads, but anyway, a small limited number of threads, and you're going to have an event loop. What happens is that you're going to have one thread whose job is just to ask the kernel, let me know if any of these events happen. And when one of those events happen, the event gets put on a queue. And then you have this single thread, which is going to go to the queue, pick up something that needs to be done. For example, there's a new connection. Takes the new connection, looks at who the client is, prepares the answer, and sends the answer. But it doesn't actually send the answer. It doesn't block. It tells the kernel, OK, I want to send this, and let me know when the send is done. And it puts it back into monitoring for events. And then it goes back to the event loop. It takes to the event queue. It takes one more thing from the event queue. For example, this client has read your response, and now it's sending another request. Anyway, it keeps going through this loop where it tries to do as much work as possible without blocking, without stopping to read files, without stopping for connections, without stopping to read data from the network. It only does things that it can do on the CPU, and then it saves state, goes to the event loop. Now, this is particularly performant because it never uses kernel resources just to stop and wait for things to happen. But it's also fairly heavy on the programmer. The nginx developers have to take care of how they save the state, how they remember who this client was. They have to remember that this request is from the same client of this request, and they have to restore all that state. It's not a pleasant way to write code. And it's not simple. And in terms of, and Go programmers prefer simple. So how does Go work? Go brings us the best of both worlds. Because when you write Go code, you don't have to worry about the event loop. You don't have to worry about the event queue. You don't have to worry about epoll and asking the kernel to let you know about many things at the same time. You just write things as if they were threads. You just start your Go routine, accept the request, block to send the answer, and then the Go routine will resume running once the client is ready to take the answer or once it comes with the next request. But what's happening under the hood? Under the hood, there's a scheduler, but the Go scheduler, which runs inside your program, inside the runtime. And that scheduler runs all that complex epoll or kernel-specific logic to have the kernel efficiently tell it which things are ready to run at each time. And so anytime you block, for example, you do, hey, I want to read this file because this is the file I want to send to this client, you just do read, and you just wait for read to return. But what's happening is that your Go routine is yielding to the scheduler. It's telling the scheduler, OK, I'm going to block here, and we don't want to block the CPU. So just take me off the CPU, but just let me know when the file is ready. Because we don't realize computers are extremely fast for a human, but there are very wide differences in latencies. Things that run on the CPUs are fast. Things that take things from RAM are fairly fast. Things that read files are slow. Things that read across the network are impossibly slow. OK, so this is what the Go scheduler does for us. It takes code that we write, which is just blocking code, and it turns it into code that behaves as if it was written with an event loop. So it takes our code that is as easy to write as threading code, and it turns it into code that is as fast as the event loop. So now we're going to go and see how we actually use this package. All of the things I told you about happen under the hood. There is a netpoll thread, but we don't have to worry about them. As we'll see, we just go on our way servicing our connection. All right, so time to start coding. The first thing we need to be able to do is accepting connections. We are writing a small server, so we want to listen on a port and an address, and we want to accept new connections that come in. We do that with the listen. Oh, it is too big. Yes. With the net listener interface. Zoom is not my friend. So we use one of the two core interfaces of the net package, the net listener interface. It simply has an accept method, and that accept method returns a connection when someone is connecting to us and an error. And then there's close for when you want to stop that, which is not something we want to do for now. So every time we run accept, we block until there's a new connection. And when there's a new connection, we get our value of type con, which is another interface, which has a read, which is IO reader, a write, a close, IO closer, IO writer, because in Go, interfaces are composable. So you don't actually have to say, hey, this implements this and this and this. You just have to implement them, and they will be compatible. And then some methods for addresses, and then methods for deadlines, which is how we implement timeouts. Very well. So we start with our program. We start with function main, like a normal main package. And we start by getting a new listener. We say that we want to use the TCP protocol, which is the same protocol that backs HTTP, for example, because we want reliable delivery of packets. That takes care of retransmitting packets that get dropped, making sure that everything comes in order. The alternative would be UDP, which does not provide those. We check errors because, of course, And then we have our listener. With our listener, we need to build what we call the accept loop, because we want to keep accepting new connections, because our server will service many clients. So for each loop, we'll get a connection by calling the accept method. If there is an error, we are supposed to check if it's a temporary error, and in that case, retry. But for now, we're just going to quit the program if we can't accept connections. And then we need to do something with this connection. Now, as we know, con is IO reader, IO writer is something we can read from to get data from the client that just connected to us, and we can write to send data back. So there is, for example, we might want to copy that data to standard error. For that, there is a simple IO function, which is IO copy. IO copy takes a destination writer and a source reader. Now, a writer can be anything that implements write. So for example, it can be a file. And standard error is a os.file. Os.file has a write method, so we can pass it as a IO writer. And as the reader, we can just pass our connection. And this will return the number of bytes and whatever error that happened during the connection. And we're just going to print completed connection with n equal decimal and error a value. OK, so this is enough to write a small program that accepts connections and copies everything that comes into the connection to standard error. So we just run it. Now, to connect to it, we can use a command line utility called netcat. Netcat is simply a Unix tool that, from the command line, opens a connection to some other port and address, and allows us to send data from the terminal. We send the data from here. It gets accepted by gets into IO copy, and goes into standard error. Now, this looks like it's working, but it has one minor problem. What happens if we try making the second connection? Because, you know, we have many clients that connect to our website, and two happen to connect at the same time. We try connecting from this one, and nothing happens. Why is that? Because now we are blocking inside copy here. And while we are blocked inside copy, we are not accepting new connections. And until we return from one of the copies by closing this connection, then we start accepting the next one and do the loop again. So what we need to do here is use goroutines. So instead, we move this code into a function that we called copy to standard error, and which will take a netcon, which is an interface, and it will do what it was doing. And every time we accept a connection, we're going to start a new goroutine simply with the go keyword and copy to standard error our connection. Now, we run this, and we can run it with two connections, and they're both running at the same time. What's happening is that the Go scheduler underneath is keeping tabs on both this connection and this connection, and as soon as one of the two sends something, flags the goroutine as runnable, puts it on a CPU, and lets it do its job, which is, in this case, read from this, write to that. Very well. So that's right. Now, what I told you about, what I showed you about blocking the accept loop seems like a fairly hard mistake to make. But while usually you're not tempted to put all your work inside the accept loop, blocking the preventing accept from running for the entire time, something that happens often is that you run accept, And then you just do a little work before going through the loop again. For example, you run accept, and you read something. For example, you read a header, because maybe this way you have the header, and you can start the goroutine with all the information it needs to start. And usually, normal clients will start a connection and immediately send some data. So you will not notice that that's broken until someone opens a connection and doesn't send anything. At that point, they're holding up your accept from running, and your server is down because nothing else can connect. This is a security vulnerability, and it happens. This was a DNS server, an open source DNS server, that was doing exactly that. It was accepting a connection and reading the request, which is very small, it's usually a single packet, before starting the goroutine that would service it. But if a client were to open a connection and not send anything, the server would go down because it would not be servicing. So, important to keep in mind that the accept loop needs to have nothing else than accept and non-blocking code, things that can run very fast without blocking on anything inside it. So to recap, we've seen how to get a listener by calling netlisten, using the listener to accept connections, and service connections using goroutines. And we've seen how we never block in the accept loop. Now, next, let's build something a bit more useful, because this was something that can copy things from the connection to the terminal, but let's build something that we could use in practice. We're going to build a small proxy. A proxy is nothing else than a small service that will take a connection, open a connection to an upstream, some other service, and take data from the client to the upstream and back from the upstream to the client. It simply sits in the middle and proxies things from one to the other entity. So for example, here we're going to make a proxy that accepts connection from a browser and opens a connection to google.com and sends that data over to google.com. But you can proxy between anything. So to do that, we're going to write a new function. And in this function, there is one more problem in the previous function that we haven't addressed. It has no timeouts. Now, I told you that goroutines are fast, and that's true. And goroutines are cheap, and that's true. But when a goroutine is holding some kernel level resource, for example, it's holding file descriptor because it's holding a connection open, it becomes precious because you don't have that many file descriptors in your system. Now, who here has ever seen error, can't accept, retrying in 1 second, run out of file descriptors? Lots of nodding, lots of pain, shared pain. Let's take a second. But when that happens, it's because you have a lot of connections open and you don't have enough file descriptors in your limit to accept new connections. Usually when that happens, either you have too much load, or more often, you don't have timeouts that just kill connections that have been open for too long. So how do we apply timeouts? Timeouts are applied with deadlines. Deadlines in Go are a hard time, an absolute time, at which either the read or the write completes, or it returns with a timeout error. But it's not idle timeout. It's not like you have to send something every 10 seconds. It's a deadline. So to use that, we're going to have to write our own copy function. So we're going to have to write a for loop where we have some buffer. It doesn't matter what size because it's just the chunks in which we're going to read and copy things over. And we're going to first do a read on the connection. So we're going to read into the buffer. And we're going to, if there's an error, we're going to just print it and return. And then we're going to do a write on our os.sStandardError of the buffer up to n, because read might not read as many bytes as there is space. It might read less, and we want to copy only up to there. OK. And then when an error happens, we're going to hit this. Now, when the connection is over, the error return will be an EOF error, end of file. Now, when that happens, we want to make sure that we close the connection. Because, for example, if the error is something else, we want to be sure that we're closing it. So now we tried this new one. Oh, of course, we wrote this to add a deadline. So now at every iteration, just before we do the read, we're going to set a deadline. So for example, we're going to say that we want the read to terminate within time.now plus, say, 5 seconds. So we want each read to terminate within 5 seconds. Now, when we run this, we will have only 5 seconds to stay idle. 1, 2, 3, 4, 5. Before the connection gets closed. This way, if a client just opens a connection and never does anything, it's not holding up one of our precious file descriptors. OK, so we've seen how to add timeouts, but we will go back not adding those to the proxy because that requires a bit more thinking. What timeouts do you really want? It depends on how much you trust the upstream, because you might want to just defer all closing connections to the upstream if you trust the connection to it, maybe if it's through localhost. Or maybe if it's a remote upstream, so you want to make sure you have timeouts on both sides of the proxy. But that's that's a matter of configuration. Now, to write our proxy, we want to copy things in both directions. So we want to be able to have our connection from the client, and we want a connection to the upstream. And to do that, we're going to use the other main function of the net package, which is dial. We use listen to accept connections, and we use dial to connect to something else. So we're going to connect to google.com at port 443, because that's the port of HTTPS. We make sure to defer closing this connection as well, so that when we're done with the proxy, we close both, because this is another way to end up without file descriptors. If you only close the downstream connection, leave the goroutine, and now there's a dangling connection open on the other side. And then we need to do copies in two directions. Before, we were just copying things from the client to standard error. Now we want to be copying things from the downstream connection to the upstream, and the other way around. Now, something you should be worried about here is that I am starting a goroutine without tracking it. That's usually a bad sign. Because usually when you start a goroutine and you don't know how it ends with you getting paged. So here it's fine, because we know that as soon as one of these two returns an error, it will, as soon as this one returns an error, it will hit the defer, and it will close both connections. Closing both connections is going to cause an error on the I/O copy as well, and it will bring down the goroutine, because when the function of the goroutine returns, the goroutine goes extinct. So now we're going to run proxy on our connections. And we're going to go to a browser. And we're going to load. Now, it looks like an error, but it's actually working. How do we know it's working? That error wasn't generated by us. That error was generated by google.com, because we just asked google.com to serve localhost. And google.com went like, I don't really host localhost. But something that we can look at is the fact that the certificate that it tried to serve is a certificate for google.com. Why? Because we are proxying the connection. We are taking all the bytes from the client, sending them to the server, and all the bytes from the server, sending them to the client. The server is sending a certificate for google.com, which of course is not valid because we are trying to connect to localhost.com. This is not some security attack. This is how things are supposed to work. But now, of course, now we've seen how to build a small proxy with Go. And what if I told you that this proxy is literally as fast as it can get? And I'm not joking. Because what happens under the hood is that io.copy is noticing that on one side, it has a TCP connection, and on the other side, it also has a TCP connection. And so what it's doing is that it's going into the kernel and telling the kernel, take these two file descriptors and just send from one to the other. And the kernel is doing all the work from there on. So it can't go any faster because the program is not involved at all. This is what nginx does. It's famous for using send file to send from files to TCP connections, and for using splice to send from TCP connection to TCP connections. Go does that magically for you by the power of interface upgrades, which are one of my favorite features, favorite patterns in Go. Inside copy, there is a bit of code that checks if either the destination or the source know how to take the other side and take care of the copying themselves. So either they have a read from or a write to method. And if they do, it takes one and passes it to the other and tells them, OK, go away and do your thing. And TCP connections know how to take another TCP connection and tell the kernel to just merge them, to just copy from one to the other. So with this simple 30 lines of code, we are using the fastest possible way at the kernel level to copy things from one connection to the other, and we didn't even notice. Isn't that nice? OK. Now, I think I have 5 minutes left. But it wouldn't be a talk of mine if there wasn't a bit of TLS. So we're going to very quickly look into how to parse TLS when things arrive and then proxy them. Now, TLS is an overly complex protocol. 20 years of legacy that built on top of each other and things that we would very much like to remove and can't. So it starts with a header, which has a type, a version that doesn't mean anything anymore, and a length. And then inside there, the first thing is a handshake, which has another type, which is different from the first type, another length, because there's a lot of lengths, and then a client hello. Inside the client hello, there is another version which doesn't mean anything anymore either. And then there's a random value, some session ID that doesn't mean anything anymore. It's bad, but thankfully, I'm not going to write a parser on stage. Instead, what we're going to do is use a parser that it wrote to extract this value. This value is the server name indication. It's what the browser sends to let the other side know which certificate to serve. In this case, it's going to send localhost, because that's what we're trying to connect. But anytime you connect to something, it sends in the first packet, in the clear, here is the name of the website I'm trying to connect to. So give me the certificate for that, if you have it. Nobody has a certificate for localhost that works everywhere. So how we're going to write that is that, first of all, we're going to need a buffer to write things into. New function. First thing first, we're going to receive a connection, defer closing the connection, and set a deadline, because we don't want to stop forever reading the client hello. That's exactly what we just said is what we don't want to be doing. So we set a read deadline of 5 seconds. And then we create a new buffer, which is a bias.buffer. and we do a read. But this time we use copy n, because we want to read just the header part of the record. So we're going to copy to the buffer from the connection, and we're going to copy 1 byte of type, 2 bytes of 1 byte of type, 2 bytes of version, and 2 bytes of length. Very well. Then, based on these 2 bytes of length, we're going to read it into the length of the entire first message, because that's what you need to do when you have variable length messages on a stream protocol. So for that, we're going to use the binary encoding package, and we're going to use the uint, the big endian encoding, and the uint16 value. So buff.bytes. Invalid type. That's unfortunate. Not when you call a method on it. It just didn't have the import. But yes, it has to be a pointer here, for example. And we don't want the first 3 bytes, so from 3 to 5. So this is the length of the next message. And again, we read the first message in the exact same way. We copy into the buffer, we read it from the connection, and we read length worth. Now that we have the entire client hello in the buffer, we're going to cheat and use existing parser. By calling parse client hello, and we're going to pass the buffer bytes. And if this worked, we're going to print the SNI, which is client hello.sni. Now, if this all works, we're going to be reading the first packet, finding the SNI value, and printing it to the terminal. Oh, fuck. Don't you dare. So we're going to reload this. It's not going to connect. It's still connecting, because we did not change it from proxy. We're going to connect. It's going to say connection closed, because we're doing nothing else after closing the connection, and it's going to tell us what it just read. Now, last part. So to recap, we're reading the header, parsing it, and printing the SNI. Now, last thing. What if we wanted to proxy the connection after we did this? Well, the problem is that to do that, we would have to copy things from the existing connection. But we already read part of the connection. So if we proxied everything from here, we're only proxying from here on, and we're not sending that important first packet over to google.com, and the connection would break. So how do we fix that? We fix that using multi-reader. And that's why it's so beautiful, that interface composition in Go. Because we can take 2 readers. For example, we can first make a little type, which is a wrapper for a netcon, and which we're going to call a prefix con. And we're out of time, so I'm going to copy paste this. Because of course I had. But I'm going to explain how it works at least. So what we're doing here is that we are creating a small netcon wrapper. So a small thing that exposes all the methods of a netcon, but also holds a reader. And then a small method to tell it which read function to use, because otherwise it wouldn't know which one of these two to use. And then we're going to use that as our new connection. After passing, I copied too much. After passing here to the multi-reader as the reader. So first is going to read from our buffer the things that we've already read from the connection. And then it's going to read everything else from the connection. And then we can just proxy that con, just like with the exact same function we were proxying the old one. Basically, we're stitching together the buffer we already had and the rest of the connection to proxy all the rest. And this is not happy because we have to proxy the new one. So if we stop this, we're going to see that it's both proxying and showing localhost. So this is actually something very useful in practice. This is what's called a SNI-based router, because it can look at the SNI and based on what website you want to connect, decide where to send your connection. And with these 56 lines, 65 lines, we've written something that has the same core feature as things like proxy. And that's all thanks to the net package. So thank you very much. And at this point, I think we have a couple minutes for questions.
What if SNI gets encrypted?
Haha. So what he's referring to is long-standing privacy issue on the internet, which is the fact that this value is unencrypted. That's why we could read it from the connection. The problem is that to encrypt it, we need to know a key for the server before we make the connection. And that's been a key distribution problem for a long time. It's getting worked on as with a way to distribute keys through DNS, such that then we would have the keys to then encrypt the SNI. But that's a new standard that's going through the IETF process. The answer is, if you own the infrastructure, you would have to decrypt TLS at your proxy, at your proxy level, completely decrypted, and then proxy maybe re-encrypting it on the other side. Thankfully, these days, TLS is extremely fast, so it's not really a performance issue anymore. The other day, I made a mistake developing the crypto TLS library in Go. I added a single allocation to reading records, and it got 30% slower. So decrypting each record is as low as doing 3 allocations in your code. And I'm sure you're not counting all the 3 allocations you do in your proxies. So stop worrying about TLS performance. It's fast. Anyone else? Questions?
Do you see any? The proxy function, when you have the goroutine that does the copy to a buffer and the other one that is there, could you have been using the net pipe function, or is because that does the interface upgrade?
So what netpipe does is that it gives you 2 netcons which talk to each other. But here what we have is that we have two netcons where one thing goes from one to the other. Well, what we're doing here is that we have 2 cons already because we have the downstream and the upstream cons, and we want to be the copy between them. So netcon would not help us here. Pipe would not help us here. If we were to, netpipe can't help us here. Also, netpipe is in memory, which is kind of weird. When you write your tests using netpipe, it does not really work like with TCP, because with TCP there are buffers. You can send a bunch of stuff, and even if the client doesn't read it all, it's going to sit in a buffer up to a certain window. While netpipe will take each write from one side and do a wait for a read on the other side. And I'm saying this because I just finished having to fix that in the crypto TLS package in the standard library.
Thanks.
All right. Yeah, time is over. Sorry. Yeah. Thank you very much.
Thank you very much.